Okay. All right, so today's lab is on distillation. So distillation is a method that's used to purify liquids, and you could use it to separate a volatile liquid from a non-volatile component. So you could use it to separate a mixture of seawater. You could separate the salt from the water. You could also use it to separate a mixture of volatile liquids. And this is achieved by taking advantage of the fact that these liquids have different vapor pressures. So these are some equations that are going to help us calculate the composition of the vapor above the mixture. The only equation you have to know is equation 1. I don't really want to scare you with the math, but I just need to show it to you so you know where I got my numbers from. So if you see equation 1, this is in your lab manual. It's actually a combination of Raoult's law and Dalton's law. And pretty much all it's saying is that the vapor pressure produced by our mixture, and let's pretend that we have a mixture of two miscible liquids, the vapor pressure produced by this mixture is equal to the mole fraction of component A times the vapor pressure of pure A plus the mole fraction of component B times the vapor pressure of pure B. Now, using
Carlos?
Yes.
For me, I can only see the first two slides. Everything else is kind of like frozen.
Okay. Thanks for telling me. You see this like this or no?
Nothing is
I still see the
changing.
same.
All right, give me a second.
Did you directly share the PowerPoint or the desktop in total?
Can you check now?
Oh, there you go.
Everyone sees that. I'm going to flip through the slides, and you guys tell me if this works.
Yeah, that works. It's just when you go into presentation.
I'm going to go into presentation. You guys tell me if it works. All right, I'm going to slides now. Does it work?
Yeah.
Yeah, now it's
working?
working. Yeah.
Okay. I'm going to start from distillation. Distillation is a purification method used to separate liquids. You could separate a liquid from a non-volatile substance like salt and water, or you could separate a volatile liquid, achieved by taking advantage of difference in vapor pressures of this. Now, we have these two equations that allow the composition of vapor of the mixture. And let's pretend we have a mixture of two miscible liquids. So equation 1 is a combination of Raoult's law and Dalton's law. It's in your lab manual.
Sorry to interrupt you again, but we're back onto like the first slide.
Okay, can you see this slide? Yeah?
There you go, yeah.
All right, we're just gonna do it like this. I don't know why presentation doesn't work, but it is what it is. So equation 1 in your lab manual, mixture, it's a combination of Raoult's law and Dalton's law. All that it says is that the total vapor pressure produced by the mixture is equal to the mole fraction of component A times the vapor pressure of pure A plus the mole fraction of component B times the vapor pressure of pure B. Now, we could also derive another relationship using the ideal gas law. And you see it's equation 2. And on the right side of equation 2, we have the moles of A divided by the total moles. And this is the definition of mole fraction of A. So what this equation is saying is that the vapor pressure produced by component A divided by the total vapor pressure produced by the mixture is equal to the mole fraction of A. So why are these equations important? So what these equations tell us is that the composition of the vapor leaving a mixture is not necessarily the same as the composition of the liquid mixture. So I'm going to use an example. So let's pretend we have a 50% benzene, 50% toluene mixture. And guys, when I say 50% benzene, 50% toluene, I mean 50 mole percent. And throughout this, every time I say percent, just keep in mind it's mole percent, not percent by volume or percent by mass. So we have this 50-50 mixture of benzene and toluene, and we could use these equations to calculate the vapor composition given off by this mixture. And what we find is the vapor composition isn't 50-50. It's actually 80% benzene. And this is great. This is what we want, because 80% benzene, if we can collect that vapor and condense it back down to a liquid, we already have significant separation right there. So this is actually exactly what we do for distillation. And here's a picture of a distillation apparatus. It's made up of a few parts. On the left, you see the thing being heated. That's the distilling flask. The condenser is in the middle. The condenser is cooled by flowing water. And on the right, we have a receiving flask, which collects your distillate that comes over. Now, for our example, let's pretend that our distilling flask is filled with our 50-50 benzene toluene mixture. We boil it. The vapors will rise up. And remember, the vapors are more concentrated in benzene. They'll rise up, they'll go into the condenser, cool down, turn into a liquid, and come down, and we will collect the liquid in the receiving flask. And this liquid will be 80% benzene, 20% toluene. Now, this is still a mixture. It's not pure in any sense, but it's better than what we first had. And if we want to purify it even further, we could actually do another simple distillation. And if it's still not pure, we could do another one and another one and another one until we get pure benzene. And we could actually predict how many simple distillations we need to do using what's called a liquid vapor composition plot. Now, this plot, it's different for every mixture, and this is a specific one for benzene and toluene. So on the y-axis, we see that we have temperature, and on the x-axis, we see that we have mole percent of one of the substances of the mixture. In this case, we use benzene. Now, we also have these two curved lines, and what they represent is the bottom curve shows the boiling point of any composition of the two compounds in the liquid. And the top curve shows the vapor composition of the vapor given off of that specific composition. So I'm going to show you how to use this vapor plot. So what you have to do is you draw a line. We already know that our liquid is composed of 50% benzene, 50% toluene. So we go to 50% on the x-axis, and we draw a line from 50% vertically till we hit the bottom curve. Now, at the bottom curve, we will draw a horizontal line towards the top curve until we hit it. And once we hit the top curve, we draw a line back down towards the x-axis. And what that tells us is when we boil a 50% mixture of benzene toluene, the vapors it gives off is going to be 80% benzene and 20% toluene. Now, let's pretend that we actually did this. We boiled it, we collected that vapor, which is 80% benzene, and we now have a liquid that's 80% benzene. Well, we don't want to stop at 80%. We want a little more pure than that. So let's do a second one. So we could do it on the plot again. And this time, since our liquid is 80%, we start at 80%. We draw a line vertically, hit the bottom curve, horizontally, hit the top curve, and back down towards the x-axis. So that tells us that if we boil an 80%, 20% mixture of benzene and toluene, that our vapor is going to be something like, I'll call it 95% benzene. That's pretty fair. So if we collect that vapor, if we condense it into a liquid, we'll now have 95% benzene. But we don't want 95%, we want 100. So let's do another distillation. So again, we do the same thing. This time we start at 95%. We go up, hit the bottom curve, go left, hit the top curve, go back down. And the vapor, when you boil a 95% benzene, 5% toluene mixture, is going to be like 99.9% benzene. And we'll stop there. We'll call that a win. But it's great. Unfortunately, we had to do 3 simple distillations back to back to back in order to achieve this separation. There's no one in the world that wants to do 3 simple distillations just to isolate benzene. And that's why they came up with a different type of distillation known as fractional distillation. So this is the apparatus for that. And fractional distillation, it's almost the same as simple distillation as far as the setup is concerned. The only difference is that fractional distillation has a fractionating column attached to it. Now, this fractionating column is just a long column, and it has inert packing in it, usually glass beads. But the idea behind the packing is you want to give the column a lot of surface area for the vapors to condense on. So what's going to happen in the fractionating column is you're going to heat your mixture. So we're going to heat our 50-50 mixture in this round bottom flask. It's going to travel up the column. It's going to condense somewhere on this column, and then it's going to re-vaporize and condense again and re-vaporize and condense again. And it's going to go up and up and up doing these cycles. And every time it condenses and re-vaporizes, the benzene will leave a little bit of the toluene behind, and the toluene will fall back into the round bottom flask. So each cycle of vaporization and condensation in the fractionating column, the benzene is getting more and more pure. And by the time it comes out to the condenser, it's nearly pure, or it is pure. Now, in order to show you exactly what's going on inside the fractionating column, I drew a very sophisticated diagram of a close-up of a fractionating column. Here it is. So what happens initially is our 50-50 mixture is boiled. Now the 50-50 mixture produces a vapor that's 80% benzene. So that's going to travel a little bit up the column, and it's going to condense somewhere. And that liquid is going to be 80% benzene, 20% toluene. It then will re-vaporize, but it's going to leave some toluene behind, travel a little bit further up the column, condense again, and this will be 95% benzene. It will then re-vaporize and condense again, and this cycle continues on until it comes out into the receiving flask. Now, what fractional distillation does is what we needed 3 simple distillations to do, it does in just 1 distillation. So it's more efficient than simple distillation by far. And according to your lab manual, it says that there are fractionating columns that have been designed to separate liquids that boil as little as 2 degrees apart, 2 degrees Celsius. And that's pretty cool, in my opinion. Now, this is pretty much the end of the lecture, but I do have to share my sources. I took a lot of this material from this YouTube channel called Chem Survival on YouTube. They do an amazing job of explaining both simple and fractional distillation. And I highly recommend you watch these videos because they explain it better than I do. And I will send these to you as an additional resource with the video that you need to watch for the lab. So I recommend that you watch them. You don't have to watch them, but they are great. And they do other lab techniques as well, and they do a really good job. So I would watch them. So this is the lecture. This is it. Does anyone have any questions, comments?
I have one, but not about the lab.
Okay, go ahead.
More or less, when do you think you're gonna get us the first lab returned to us? Because since we're gonna be returning another one, I feel like it would be good to get the first one back, just to see what, like, our mistakes or what we should improve on. So
usually when we do these labs, you get the lab report back graded at the beginning of the next lab session. But since people are still trying to get a feel for how to write these reports and the feedback is crucial at this point, I'm going to try to give it back earlier, but that's not a promise. I have a lot of feedback to give. I have like 24 reports to grade, which isn't terrible, but it's not as easy as it sounds. So that's the best answer I could give you. I'll try to give it back early.
Okay, thanks.
Does anyone else have a question? Comments on my sophisticated diagram?
You did great.
Thank you, thank you. Anyone else? Serious questions?
that diagram is very sophisticated. Really made me understand everything.
I appreciate it. All right, well, if that's everything, guys, have a good one. I'm going to email out the video now, and I'll also send the recording as soon as I upload it to YouTube.
Okay, thank you.
All right,
Thank you.
everyone.
Have a nice day.
Have a good day.
You too. Have a good one.
Thank you.
I have a quick question.
What's up?
The website you gave us the first lecture for the physical constants. I think some people already told you it's not working.
Yeah, I heard that. I haven't been able to take a look at it, but you don't have to use that website. You can just go on Wikipedia, Google, or anything to get it. But I'm going to see what's up with it. I'm going to try to get it working, and if I can, I'll let you know how I fix it.
Okay. Also for the lab reports, I know for like my Gen Chem labs, if there was any kind of like data table or anything in the lab manual, like they would want us to like copy that and put it on our report. Do you want that too, or only like put the lab, like the graphs and the data tables that?
No, that you make the data tables. The data tables is not part of your pre-lab. For Orgo labs, there's no real data tables. You kind of make them yourself, and that goes in the results section of the lab report.
Okay, so we don't have to like copy any that they have on there already.
I mean, if it makes it easier for you, you can, but you don't have to. You can make your own.
Okay, thank you.
Anyone else?
Oh, yeah, I have a question. So should I send you my pre-lab for the distillation since I did like just the pre-lab for the other one? So when I send the finished lab, do you want the pre-lab for this one too?
Yes, send it to me.
Okay, thanks.